For crude oil to be used effectively by modern industry, it has to be separated into its component parts and have impurities like sulfur removed. The most common method of refining crude is the process of fractional distillation. This involves heating crude oil to about 350 degrees Celsius to turn it into a mixture of gases. These are piped into a tall cylinder known as a fractional tower. Inside the tower, the very long carbon chain liquids such as bitumen and paraffin wax are piped away to be broken down elsewhere. The hydrocarbon gases rise up inside the tower, passing through a series of horizontal trays and baffles called bubble caps. The temperature at each tray is controlled so as to be at the exact temperature that a particular hydrocarbon will condense into a liquid. The distillation process is based on this fact. Different hydrocarbons condense out of the gas cloud when the temperature drops below their specific boiling point. The higher the gas rises in the tower, the lower the temperature becomes. The precise details are different at every refinery and depend on the type of crude oil being distilled. But at around 260 degrees, diesel condenses out of the gas. At around 180 degrees, kerosene condenses out. Petrol or gasoline condenses out at around 110 degrees, while petroleum gas is drawn off at the top. The distilled liquid from each level contains a mixture of alkanes, alkenes, and aromatic hydrocarbons with similar properties, and requires further refinement and processing to select specific molecules. The quantities of the fractions initially produced in an oil refinery don't match up with what is needed by consumers. There is not much demand for the longer chain high molecular weight hydrocarbons, but a large demand for those of lower molecular weight, for example petrol. A process called cracking is used to produce more of the lower molecular weight hydrocarbons. This process breaks up the longer chains into smaller ones. There are many different industrial versions of cracking, but all rely on heating. When heated, the particles move much more quickly, and their rapid movement causes carbon-carbon bonds to break. The major forms of cracking are thermal cracking, catalytic or CAT cracking, steam cracking, and hydrocracking. Because they differ in reaction conditions, the products of each type of cracking will vary. Most produce a mixture of saturated and unsaturated hydrocarbons. Thermal cracking is the simplest and oldest process. The mixture is heated to around 750 to 900 degrees Celsius at a pressure of 700 kilopascals. That is around 7 times atmospheric pressure. This process produces alkenes such as ethene and propene and leaves a heavy residue. The most effective process in creating lighter alkanes is called catalytic cracking. The long carbon bonds are broken by being heated to around 500 degrees Celsius in an oxygen-free environment in the presence of zeolite. This crystalline substance, made of aluminium, silicon, and oxygen, acts as a catalyst. A catalyst is a substance that speeds up a reaction or allows it to proceed at a lower temperature than would normally be required. During the process, the catalyst, usually in the form of a powder, is treated and reused over and over again. Catalytic cracking is the major source of hydrocarbons with 5 to 10 carbon atoms in the chain. The molecules most formed are the smaller alkanes used in petrol, such as propane, butane, pentane, hexane, heptane, and octane, the components of liquid petroleum gas. In hydrocracking, crude oil is heated at very high pressure, usually around 5,000 kilopascals, in the presence of hydrogen with a metallic catalyst such as platinum, nickel or palladium. This process tends to produce saturated hydrocarbons such as shorter carbon chain alkanes, because it adds a hydrogen atom to alkenes and aromatic hydrocarbons. It is a major source of kerosene jet fuel, gasoline components and LPG. In one method, thermal steam cracking, the hydrocarbon is diluted with steam and then briefly heated in a very hot furnace, around 850 degrees Celsius, without oxygen. The reaction is only allowed to take place very briefly. Light hydrocarbons break down to the lighter alkenes, including ethene, propene and butene, which are useful for plastics manufacturing. Heavier hydrocarbons break down to some of these, but also give products rich in aromatic hydrocarbons and hydrocarbons suitable for inclusion in petrol or diesel. Higher cracking temperature favors the production of ethene and benzene. In the coking unit, bitumen is heated and broken down into petrol alkanes and diesel fuel, leaving behind coke, a fused combination of carbon and ash. Coke can be used as a smokeless fuel. Reforming involves the breaking of straight-chain alkanes into branched alkanes. The branched chain alkanes in the 6 to 10 carbon atom range are preferred as car fuel. These alkanes vaporize easily in the engine's combustion chamber without forming droplets and are less prone to premature ignition, which affects the engine's operation. Smaller hydrocarbons can also be treated to form longer carbon chain molecules in the refinery. This is done through the process of catalytic reforming. When heat is applied in the presence of a platinum catalyst, short carbon chain hydrocarbons combine to form aromatics used in making chemicals. A byproduct of the reaction is hydrogen gas, which can be used for hydrocracking. Hydrocarbons have an important function in modern society, as fuel, as solvents, and as the building blocks of plastics. Crude oil is distilled into its basic components. The longer carbon chain hydrocarbons may be cracked to become more valuable shorter chain hydrocarbons, and short chain molecules combined to form useful longer chain molecules.